So this video is going to start with talking about the periodic table, and we're going to be looking at the different groups of elements that are on the periodic table, the big groups and the individual groups, and their characteristics, and what we might use some of them for. So starting off, what information can you find on the periodic table? So we've already seen some of this talking in earlier lectures. So you can find the atomic symbol. So that is the letter or sets of letters that represent an element. In a lot of periodic tables, including the one that I've posted on Go Studio with this lesson, you can find the element's name. Some of them, like the one that you see here, don't have the element's name, but a lot of them do. They will always have the atomic number, again, that number of protons that are found in the element, and then the atomic mass. So the atomic mass, again, is usually the bigger number. That's usually, well, it's always the bigger number, except for hydrogen, and it's usually a decimal point because it's got that, it's the average of the isotopes. And it's organized in a very specific way. And so that's one of the big things we're going to be looking at in this video. So the first thing to take a look at is, here's our periodic table all laid out. And this one's color coded like the one that I've posted. And what I want you to notice is what most of the elements are on the periodic table. Because most of the periodic table elements belong to one specific group. And you probably have figured it out by now, and that is most of the elements are metals. So the orange stands for metals. We've got a few what we call metalloids or semiconductors. We've got a handful of nonmetals, but most of them are metals. These are the ones that are gray are not yet confirmed. A couple of them have been confirmed. But like I said, there's 118. And so we've got this wide variety of metals. You can see pictures of some of them up here. Some of them are liquids, solids, used for a variety of materials. Most or some of you may have worked with some of these. If you've done jewelry working or any sort of metal working, you've probably worked with some of the ones that are on here. Again, if you've done jewelry work, you may have worked, with some version of carbon. And then helium, like I mentioned, these guys are we know these guys from balloons. If you're not already aware, though, we are in a helium shortage. It's really hard to find helium right now because helium, as you can see here, is a byproduct of radioactive decay. And we've tapped most of the natural stores of helium. So any helium that we've got coming in right now is from industrial processes. And then we've got nonmetals that are also gases, liquids, and solids. So we're going to look at these different groups. So we're going to look at the big groups first, and then we're going to look at individual, what we call families. So we're going to start first with the metals because they are the biggest group. These guys are shiny, opaque, and as we've seen in previous videos, they are good conductors, both of heat and electricity. Because they've got those loose electrons. So what else do metals have in common? So metals are malleable. This means that we can hammer them into shapes without breaking them. And so you're probably familiar with this idea, right? You can take things like iron, steel, copper, gold, and you can put them into different shapes, not just by heating them, but also by hammering on them. Now, the different metals vary in how tough they are, but they can all be hammered without breaking their structure. They are also all ductile, meaning that they can be drawn into wires, and this makes them very useful for things like electricity. The ones that are highly conductive, we've been able to draw into wire to be able to use for conducting electricity in our homes and so forth. But again, those of you who may do, because I've seen in some of the discussions, some of you do jewelry work, this has been extremely helpful as far as doing that. So these guys are generally solid at room temperature. So you can see different examples of all these guys. So we got barium, strontium, magnesium, beryllium, calcium. Calcium is a metal. I know that's a surprise to a lot of people. We've got radium. That one is radioactive, hence the name. Variety of them over here. We've got copper, lead. This is either silver or zinc. It's hard to tell. I'm going to guess it's silver because zinc is usually a little more dull. That there are exceptions. So mercury, gallium, cesium, and francium are going to be liquids at room temperature. So mercury was on the previous slide. It's always going to be a liquid at room temperature. Gallium, this one, it depends on what the room temperature is, on whether it's a solid or a liquid. You may have seen the disappearing spoon trick. And the disappearing spoon trick is done with gallium because it has a very low melting temperature compared to other metals. So you can make it into a spoon and then you can actually melt gallium with your body heat, which is unusual for a metal. And the other one that most people don't realize is actually designated as a metal. So if you look back at the periodic table, it's designated as a metal and a non-metal is hydrogen. Because hydrogen will act as a metal, but only under very, very high pressure. So normally it is a non-metal, but under very, very high pressure, it will act as a metal. Then you've got the non-metallic elements. So these are the ones that are on the far right-hand side in that group that on the one that we just saw a little bit ago are pink in the slides. So these are on the right-hand side of the periodic table. These are poor conductors of electricity and heat. So some of these can be used as insulators. Some of them are made into compounds. So combinations of elements to be able to be insulators because of that poor conductivity. Some of them may be transparent. So you can see here we've got opaque versions, sulfur. Of course, I can't remember what that one is now. This one is coal, but this is diamond. These are both made out of carbon. And then up here we've got chlorine, bromine, and iodine. So depending on the element and depending on its form, they can be either opaque or transparent. These are not malleable or ductile, so you cannot turn a non-metal into wires. And if you try to shape these in with a hammer, like if you whack a chunk of coal with a hammer, it's going to fall apart into pieces. If you can find a hammer hard enough to whack a diamond with, it will fall apart into pieces. So you cannot hammer non-metals into any type of shape. So they will shatter if you hammer them. And at room temperature, they are a variety of phases. They can be solid, liquid, or gas. And you can see that very clearly with this set up here. These guys are actually all in the same group, not just non-metals, but we'll see they're actually related. And the chlorine is a gas, the bromine is a liquid, and iodine is a solid at room temperature. So we've got wide variety for the non-metals. And then examples of each, yeah, I just did those. The last group is what we call the metalloids. Sometimes they're called semiconductors. And these are the 6 elements that lie between the metals and the non-metals. So on that periodic table we started with, they were green. And they have a combination of properties. So they are brittle and non-malleable, but they're weak electrical conductors. And so you can see some of them I have over here: silicon, germanium, arsenic. So they have characteristics of nonmetals, but they have characteristics of metals, hence metalloid. And so silicon, Si, is a really good example of a metalloid, because you may or may not realize that you probably, well, if you have a laptop with you right now, you have some silicon in your lab. Because what is silicon used in that conducts electricity? And that would be computer circuit chips. This is why Silicon Valley in California is called Silicon Valley. That's where the first computer chips were manufactured in large amounts. And silicon is the material that's being used to conduct the electricity in those silicon chips. All right, so let's talk a little bit about the organization of the periodic table. So why is it periodic? Why does it have that as part of its name? So the periods are the horizontal rows on the periodic table. So the ones that go back and forth. And they're numbered 1 through 7. So the first period is the top row down to the 7th row at the bottom. Then we have families. So families, sometimes they're called groups. And these are the columns, the up and down portions of the periodic table. And the elements that are in a family or a group together have similar properties. So they're going to have very similar ways of reacting with things. They are going to have similar reactions, for example, with organic material like ourselves. So that's why they are actually put in those columns, because they have these similar properties of chemical reaction and physical properties. So let's take a look at the periodic table to see this. There's also an organization of what we call A elements, group A elements, and group B elements. So if you look across the top of the table, you'll see that the group numbers for the columns say 1A, 2A, and then we've got 3B, 4B, and so on. So the ones that are A are what we call the representative elements. So we've got A here, so 2 A columns on this side of the table, and then the other A elements are on the right-hand side of the table. The B elements are all of the ones here in the middle, as well as these 2 lines down here at the bottom. These guys, especially right here, are called the transition elements. So these are transitioning from these 2 to these ones over here. All the transition elements, as we'll see, these are all metals, and they all have similar characteristics. So these groups or families have traditional names. So we'll be going through these, but just so you can see how they're laid out. So you can see we've got group 1, alkali metals, group 2, alkaline earth metals, then the section there in the middle of the transition metals for the B group. These guys over here, 13, 14, 15, they don't have common names for their groups. They've just never been given common names. The first section of 16 are called chalagens, so we'll see those. And then halogens for 17, and then 18 are the noble gases. So let's jump in and start talking about a couple of these families. So we're just going to briefly go through each family so we can take a look at who's there and what their general properties are. So alkali metals, these are interesting. They are in the first column, so they're 1A. These are shiny, low-density soft metals. So if we take a look in the picture up here, these are things like lithium, sodium, potassium, rubidium, cesium, francium. The lower ones you're probably not as familiar with, but the upper ones might sound familiar. And what's interesting with these, and that's what this picture down here is for, these elements all react violently with water. That's one of their characteristics. And so this one is, I believe, either lithium or sodium. The lower you get on the column, So as you go higher in the atomic numbers, the more violent this reaction gets. These free elements of these guys are not found in nature. So you can't find in nature a lump of lithium or a lump of sodium. They're always bound to other elements. So for example, sodium, you commonly would find it bound to something like chlorine. And hydrogen is not considered an alkali metal because it only has a single outer electron. So we'll see that these guys, when we look at their electron configuration, how their electrons are organized, these guys have more than one electron shell. And so hydrogen only has that one little electron, which is part of why it doesn't function as a metal. We'll look at group 2. So group 2 are the alkaline earth metals. These guys are also soft reactive metals, but not to the extent of alkali metals. So these guys don't like catch fire when they are exposed to water or explode, but they are reactive. So again, these guys are not found by themselves in nature. So you're not going to find generally, any of these elements by themselves. They are going to be reacted with other things. And the reason why they have alkali earth metals as their name is because if you expose these to fire, they don't melt or change, unlike other metals. So like the transition metals, melt, that's how we form them. But these don't, they didn't melt or change. And so alchemists at the time named them earth metals because earth indicated that they didn't change. Big part of that has to do with the fact that they were bound to other materials. The alkaline part is related to the fact that these guys actually were used to make soaps. The parts of them that were exposed to things like fire and other reactions, they created alkaline materials, and that means that the pH was really high, and that's actually what makes up our soaps. So you can use alkaline earth metal materials as soaps very often. All right, so we'll stop there and pick up with the transition metals in the next video.